Group 7 elements present a severe physical contrast. Pale yellow gases swirl violently, while matter further down the group condenses into a rigid gray solid. These elements occupy the second column from the right on the periodic table, a family classified as the halogens. Reading from top to bottom, this group consists of fluorine, chlorine, bromine, iodine, astatine, and tennessine. Observing them at room temperature reveals a macroscopic trend. Fluorine and chlorine exist as gases, bromine as a heavy liquid, and iodine as a solid. Moving down the column, each successive element packs on more mass. The molecules become heavier, denser, and structurally tighter. Yet this increasing physical cohesion occurs alongside a sharp decline in chemical power. The heavier the halogen, the less reactive it becomes. This presents a mechanical contradiction, an elemental family that grows physically stronger while simultaneously becoming chemically weaker. Both the physical states and the chemical volatility of the halogens are dictated by a single, scalable subatomic variable, atomic radius. This is the subatomic architecture of a group 7 nonmetal. Regardless of its total size, every halogen possesses exactly 7 electrons in its outermost shell. Stability requires the atom to acquire one final electron to complete this outer ring. Capturing that electron transforms the neutral atom into a negatively charged ion, specifically known as a -1 halide. In their pure elemental state, halogens solve this deficit by bonding with each other. Two identical halogen atoms will overlap their outer shells and share a single pair of electrons. This creates a stable diatomic molecule. This single covalent bond is the default state for halogens in nature, represented by formulas like F2 or Cl2. Understanding this foundational two-atom structure is necessary to calculate how these elements interact in macroscopic quantities. When we scale up to bulk matter, we must examine the interactions between thousands of these identical pairs. These molecules are held together by intermolecular forces, invisible tethers that create friction and attraction between separate units. As you move from fluorine down to iodine, each subsequent element adds an entire new shell of electrons. With every added shell, the atomic radius expands, and the relative formula mass of the molecule increases. This increase in mass and size directly determines the strength of the intermolecular forces. Larger, heavier molecules generate significantly stronger connective tethers. Severing thicker intermolecular tethers requires more heat. Heavy iodine molecules demand immense thermal energy to break apart, whereas small fluorine molecules scatter easily. This rising threshold for thermal energy is why melting and boiling points increase predictably as you travel down the column. The transition from a gas to a dense solid is a physical consequence of increasing relative mass and tightening intermolecular forces. Chemical reactivity is governed by rules separate from physical state. To trigger a chemical reaction, specifically to form salts, a halogen must successfully capture a foreign electron. The mechanism for this capture is the electrostatic pull generated by the atom's positively charged nucleus. As atomic radius increases down the group, the outermost shell is pushed further away from the nucleus. Inner layers of electrons physically shield the nucleus from the outer boundary. This increased distance and interference weakens the nucleus's ability to exert electrostatic attraction on outside electrons. Fluorine's compact radius gives its nucleus a strong grip on passing electrons. Iodine's larger radius results in a weak, easily disrupted pull. The core chemical rule of Group 7 is that a larger atomic radius creates weaker electrostatic attraction and lower reactivity. Displacement reactions serve as the laboratory test to prove this hierarchy of electrostatic power. Displacement follows a strict rule. A more reactive, smaller halogen will forcefully evict a less reactive, larger halogen from an aqueous salt solution. Consider the reaction between chlorine gas and aqueous potassium bromide. In the solution, a potassium atom is bonded to a bromine atom, having surrendered an electron to form a stable salt. A diatomic chlorine molecule now enters the system. Chlorine sits higher in Group 7, meaning fewer electron shells and a smaller radius. Consequently, its nucleus exerts a superior magnetic pull on the contested electron. Chlorine severs the bond, forming potassium chloride, while the ejected bromine returns to its diatomic state. Displacement reactions are predictable equations of subatomic physics, entirely determined by the atomic radius of the participating atoms. This matrix summarizes the behavioral spectrum of halogens. Moving down the group stacks electron shells, building mass and driving up boiling points until gases condense into solids. Simultaneously, added shells create geometric distance, insulating the nucleus and causing reactivity to plummet. Every macroscopic behavior of group 7 elements is dictated by subatomic geometry. Predicting the state of matter at room temperature or calculating the outcome of a displacement reaction depends on the radius of the outer shell.